Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we will discuss about the review of the journal about geomorphology and hydraulic phenomena. The title of the journal is Bank Erosion under the impacts of hydraulic erosion, river stage change, and revetment protection in the middle of Yangtze River. So this journal, published by Geomorphology, and the publisher is Elsevier, and then the index of the H index of this journal is 193, and has the quarter of Q1 from Simaku Junior. Okay, so this study discusses riverbank erosion along the middle Yangtze River caused by hydraulic erosion. The analysis uses a numerical model to simulate stress and seepage on riverbanks, confirming the correlation between tensile stress on revetment structures and changes in river stage conditions, along with field observation. Due to significant channel erosion, around 10 to 1,010 cases of dike revetment collapse have occurred, covering approximately 729.5 kilometers from 2003 to 2020. So extensive revetment work has been done, but covering around 1,500 kilometers to stabilize the river morphology, equivalent to 37% of the total riverbank length, about 4,000 kilometers for the total, and 84% of the total eroded riverbank length. So in the left, we see that the erosion for the revetment and riverbank erosion in Yangtze River, in the middle of Yangtze River. So the data sources of this study, which are hydrological data and cross-sectional profiles, daily average hydrological data, water discharge and river water levels, and then cross-sectional profiles. So this data forms the basis for quantitative analysis of riverbank erosion processes. And the topographic measurements also were conducted in April, August, and November 2020 to depict and analyze the evolving dynamics of erosion near riverbanks. And the second data is sediment characteristics and revetment design. Samples were taken from selected location and sediment grading was measured with a laser particle size analyzer. The tools called MicroTrack S3500 and based on grain size variation, three general layers were identified. One is upper clay sediment layer, 0.03 millimeter, about 4 to 5 meters thick in the land, and also middle slightly coarser silty land layer, 0.11 millimeter. So this is between 6 and 40 meter thick in the field, in the land, and then also lower slightly finer silty sand layer, 0.06 millimeter. And the third data is groundwater level measurement near riverbanks and to monitor changes in groundwater level. So a well was built in that area, positioned 10 meters from the floodplain boundary. The well is 20 meters deep and then 9 meters lower than the lowest recorded level of 24.5. So this is to ensure the well stays above flood levels, elevated 1.25 meter above ground level and reinforced with iron. This is the graphic and the picture about the data of the silt and clay and the grain size and the data. And you can see the graphic that in the middle is silty sand and the upper is silty clay and the lower also particularly kind of land. And then the groundwater surface measurement near riverbanks. So to monitor groundwater level changes, a well was built positioning 10 meters away from the edge of the floodplain. The well has a depth of 20 meters below ground level, with the bottom of the well situated approximately 9.0 meters lower than the recorded lowest river level of 24.5 meters. So to ensure the well remains above water during floods, its top is elevated 1.25 meters above ground level and reinforced with iron. So you can see the picture in the right position with the blue one. So this is the reinforce of the groundwater for the groundwater surface perimeter. And numerical modeling of ground stress variation to investigate the stress strain behavior of riverbanks. Two different models were used in GeoStudio 2018. First one is SIP-W, a two-dimensional unsaturated flow model. And then second one is Sigma W, a two-dimensional finite element stress deformation model. So the basic equation governing flow movement are based on Darcy's law and mass conservation principle. In the figure of the slide, we can see the schematic diagram of bank cross section applied in the numerical model, showing boundary conditions and mass discretization. Note that triangular and quadrilateral meshes are used for calculations, and the mesh in this figure is only a generalized representation. So we can see that the position and for the modeling in the software of GeoStudio. And then for the result of analysis, one is topographic changes. The comparison of topography before, during, and after flooding is illustrated in the image below in the next slide, showing that the topography near the river bank offer a basing length of 5.4 km and width about 500 meters, half of the total river width. And during the pre-flood period, April to August, sediment deposition occurred along the riverbed near the bank, with an average deposition depth of around 0.45 meters and a maximum deposition depth of 10.7 meters within 4 months. During the post-flood period, August to November, signs of erosion were observed near the riverbank, with an average erosion depth of around minus 1.02 meters and a maximum erosion depth of minus 10.6 meters within 3 months. Hydraulic erosion emerged as the primary factor affecting topographic changes and posed a significant impact on river protection stability. So this is the picture that I discussed before. We see in the first picture that in the river stage of 27.1 meter in April 24 and 2020, and the second one is August 22 in 2020, and then the third one is November 8 and 2020. So we can see that the difference, the blue one from those picture along to November and 2020, the blue ones is bigger than before. It seems that the flood period, and then the picture below in April to August and then August to November. So you see that the picture below in right below is more blue than the second one in the left. So this is show that the during the flood period, the riverbank collapsed in condition. Okay, so the impact of protection works in riverbanks. The effect of riverbanks protection work is evident in effectively limiting lateral retreat of riverbanks while increasing riverbed depth near the bank. So we used in section Jing 97 in the slide before. Riverbed incision depth near the bank reached 4.9 meters during 2016 to 2020. In section G 98, the maximum incision rate was 1.53 meter during 2013 to 2016, with a total incision depth reaching 4.6 meters. Riverbank deepening creates stability risk for natural embankment, and generally this is a result of flow contributing to sediment slip along natural riverbanks. However, in protected riverbanks, topographic changes can lead to damage to the riprap. So we can see in this figure that uh, with the orange line in 2002, we see that uh, the river bank or the revetment is in good condition in 2002, and then we see the difference in 2020. It became far away from the river. From the top figure, we knew that the river bank or the revetment moved to 187 meters along with the water of the river. And then the figure of the figure in the below, we can see that the river bank moved to right position along way to the water level of river is 426 meters. But we also in this graphic or in this figure, we also knew that even it move away from the water, it move away from the river, it also have a scoring in the foundation of the riverbank. We can see that the green line is deeper than the orange one. So this is occur when the water hit the river, hit the riverman or the riverbank. So the image below illustrates the average total stress distribution calculated using sigma W. So we can see the ground stress distribution. So in the left, this is under the tension, and then the right is under compression. So it means that the riverbank in the outside the what is it the outside the revetment has under tension force, and in the riverbank which have the water has the under compression. So we see the graphic in this figure. Okay, so from the graphic that I said before, we can see the failure of the riverbed structure when it comes a big flood. It become the structure become collapse. However, we have we have a process of the structure to collapse. So crack formation can be classified into two aspects: tensile stress concentration during seepage erosion stages between different soil layers. First one is location of peak tensile stress on revetment surface. The peak tensile stress location on the revetment surface depends on river stages. So this before, during, and after floods. Consequently, revetment strength on the bank surface is more vulnerable to damage in areas where water level fluctuations occur most frequently. So this phenomenon is influenced by the rate of water level rise and sediment properties of the riverbanks. So as I did before in the slide before this. So specifically, if sediment layers, especially clay, show lower permeability and higher compressibility, the revetment structures becomes more susceptible to increased tensile stress during periods of rising and unevenly decreasing water levels. This also suggests that river water level fluctuations can impact revetment structure vulnerability and stability. So in the second condition is typical location of cracks. These cracks are often formed at the interface between two different layers. Different layers, I mean, in the solid, two different layers of soil, which are also relatively concentrated locations for groundwater seepage. Each year during the dry season, groundwater causes dissolution and loss of some riverbank materials. Weakening embankment of riverbank structure increases the likelihood of crack formation, especially in areas where sediment layers have different properties and more prone to differential settlement. So you can see the picture here that stage 1 is localized subsidence, and then stage 2 is expansion, and then stage 3 is failure of the structure. So we see also the graphic that in dry season and in rising flood and recession, 49% of the failure during the flood has happened in Yangtze River, the middle of Yangtze River. Okay, so next slide is stages of revetment structure failure. Stage 1 initially damage and tensile stress cracking that I said before in the first in the slide before. Location of crack and slow development. And then during the early stage of river level rise, revetment protective layer on the riverbank surface experiences localized tensile stress. This stress often exceeds the tensile strength of the material, leading to initial cracks. Stage 2, local collapse. So crack widening. Over time, initial cracks deepen and widen due to cumulative effects like groundwater seepage and localized stress concentration. Groundwater seepage in particular can wash out fine particles from behind the revetment, creating cavities and weakening the foundation. And the second one is cavity formation. Cracks can evolve into cavities or small collapses in the revetment. And then the third one is localized failure. This stage often appears as small-scale collapse along the riverbank. And stage 3 is large-scale collapse. So we can classify it with three items. Impact of flood periods. If local damage is not addressed, it can expand during high flood periods. And the second one is massive failure. Local failure eventually leads to large-scale riverbank collapse, where significant portion of the bank, along with protective dikes, collapse. And the third one, last one, is damage progression. This mass failure can occur in short period, especially during the recession phase after floods when the bank is weakened and outward groundwater seepage is strong. So in the figure, we can see that temporal changes of the in-channel water level and the ratio of the maximum tensile stress. We can see first and second. We can see the compressive and tensile force, and this is how I explain that the large-scale collapse happened. Okay, the last one is factor influencing failure. So sediment properties, the properties of riverbank sediment significantly influence the stages of failure. Clay-rich banks with lower permeability are more prone to stress concentration and cracking, while sandier banks may experience erosion due to faster seepage. And then the second one is river water level change rate. Rapid rises of drops in river level can increase the likelihood of stress, concentration, and seepage erosion, accelerating the progression from initial cracks to large-scale collapse. Overall, protected riverbank failure is a progressive process. So it's a progressive process, beginning with small cracks during stress concentration periods, advancing to local collapse, and culminating in large-scale riverbank retreat. Each stage builds upon the previous, making early detection and repair crucially for maintaining riverbank stability. So the main key is progressive process. So it not happen in just one day or it is a progressive process. Okay, the conclusion is hydraulic erosion during the flood season remains a primary factor influencing riverbank erosion processes. Riverbank protection works reduces lateral retreat, but it increases riverbank depth near the bank. So I said it before in the graphic. It showed that in 2020, the graphic is deeper than the year before. And maximum tensile stress on revetment surface is consistently closely related to river water levels. This relationship may due to rapid water level rise and partial saturation of sediment. So after the rise of water level, it also have an impact to the strength of the structure of the revetment. And the second one is revetment structure failure starts on the surface and then develops into significant collapse due to the direct impact of fluvial erosion. Initial cracks can be triggered by localized tensile stress concentration. And the fourth one is if riverbank sediment layers such as clay exhibit lower permeability and higher compressibility, revetment structures become more vulnerable to increased tensile stress during rising water periods. Damage is also more likely in areas where the river surface frequently fluctuates. So the fluctuation of the water level is very have significant impact to the structure of riverbed. Okay, following the operation of three Georges dam, the increased rate of changing, approximately 1.6 to 2.5 times, has raised the risk of revetment damage along the middle Yangtze River. During dry and rising water periods, river banks tend to remain stable with local damage caused by higher stress concentration. However, during and after flood periods, bank failure patterns are primarily driven by increased lateral water pressure, outward infiltration pressure, and reduced sediment strength, resulting in sediment decline or loss rather than increased tensile stress. So we can see the picture that it is drawdown and rising, and the picture in right and it is drawdown and rising. So we see that the difference 2000 and 2002 and 2003 to 2021, it increased and it increased the difference. So the fluctuation of the water level of the river has impact to structure of the river bed. Okay, so to gap analysis and recommendation for the next research, first one is long-term effects of river management process. Long-term analysis is necessary to understand the cumulative effects of river flow regulation due to dam infrastructure operation on erosion patterns and riverbank failure in various sections of the Yangtze River. Further research could be conducted by monitoring riverbank erosion over a more extended period to assess its sustained impact. And the second one, seasonal and climate variation analysis. This study focuses on specific flood and recent periods, but analysis that accounts for seasonal variation and climate change could enhance the understanding of erosion dynamics under different weather conditions. For example, during extreme drought condition, reduced water flow may have a different impact on riverbank and riverment stability. And the third one, sediment transport dynamics. The dynamics of sediment transport during high flow condition need further exploration. Integrating sediment transport models into the study could provide a better understanding of how sediment transport and deposition affect the resilience of revetment structure and riverbed erosion patterns. And the last one is comparative analysis with other river types. Further research could be conducted by comparing findings from Yangtze River with data from other rivers that have different sediment composition, flow patterns, and human intervention. This could have ideas, principle of riverbank erosion, and effective protection strategies for diverse conditions. So I think that's all. Thank you very much. Have a good day.